So the next property we're going to talk about is time reversal, as you can see. So once again, so what we're interested in is if x of t has a Fourier series decomposition is of k, x of t, of course, is periodic. The question we want to answer is, what are the Fourier series coefficients associated with the time reverse version of x? So if the Fourier series coefficients of x of minus t is b sub k, we want to find out what the Fourier series coefficients b sub k's are. Of course, it should be clear that x of minus t is also going to be periodic, and the period for x of minus t is not going to change. So let's do this exercise. The way I'm going to go about this is to use the analysis equation. In order for me to determine what b's are, so b sub k's, I'm just going to use the analysis equation directly. However, instead of integrating over one period, let me just take it from 0 to t for ease of analysis and ease of understanding. And this is x of minus t, because that's what I'm trying to find the Fourier series coefficients of, e to the minus j k omega naught t dt. Now, in order to relate this to a's, I'm going to make a change of variables once again, so if I let the new variable tau be equals to minus t, then b sub k's are given as 1 upon t, and this is x of tau e raised to power plus j k omega naught tau, and dt is going to be equal to d minus d tau. So this is d tau, and there's a minus sign outside. And as far as the limits are concerned, when t equals 0, tau is 0. When small t equals capital T, tau equals minus t. So you have the integration limits are from 0 to minus t. Now I can pull this minus sign here inside of it by changing the limits of the integral. So what I get is this is equal to 1 upon t minus t to 0 x of tau e raised to power plus j k omega naught tau d tau. Now, one of the things you observe is that this integration, once again, is over one time period. So what I can write this as b sub k is equal to 1 upon t integral over one period, which is capital T, and this is x of tau and e raised to power. So there's a plus sign here. What I need is a minus sign in order to get something which is close to the analysis equation, and that's, so there's a minus. If I pull the minus sign out, so j times minus k omega naught tau d tau. So there you have it. So what you can clearly observe is that this expression is something which looks very, very close to A's, the expression for A's, except that there's a minus k here, right? So what I conclude is this is nothing but A of minus k. So our conclusion is what? The conclusion is that B sub k's are actually equal to A minus k. In other words, if what we're saying is, if I flip the Fourier, if I flip the periodic signal in time, the Fourier series coefficients are also going to be flipped. So the next property we want to talk about is time scaling. Once again, if x of t is a periodic signal with the period t and frequency omega naught, and it has Fourier series decomposition to a sub k's, what we want to answer, the question we want to answer is, what happens to the Fourier series coefficients of this time-scaled version of x. So what happens to the Fourier series coefficients of x of alpha t, where alpha is a real number. As you may have noticed, x of alpha t is either a compressed version or expanded version of x, depending on whether alpha is greater than 1 or is greater than or is less than 1, between 0 and 1. And as opposed, so one of the things you should observe is that as opposed to the previous properties that we've seen, the period of x of alpha t does not remain the same as that of x of t. In fact, it is scaled by alpha. So what I'm saying here is that if this x of t has a period of t, and corresponding to this is a frequency of omega naught, the period for this changes to t by alpha, and the frequency, as you can verify, changes to alpha omega naught. So depending on what alpha is, there's a change in the period as well as the change in the frequency is either increases or decreases. So how do the Fourier series coefficients change? The way I'm going to do this is through the synthesis equation directly. So I know that if x of t has a Fourier series decomposition given by this expression, k equals minus infinity plus infinity a sub k e raised to power j k omega naught t, this implies that x of alpha t is just simply going to be the same expression, except that I'm going to replace t with minus t. So alpha t, sorry. So this is j k omega naught alpha times t. Let me regroup these things a little bit. And so what I here, I can write this as a sub k e raised to power j k, and this is alpha omega naught times t. So this is what x of alpha t is. So from this expression, what I observe is that x of alpha t does have a Fourier series decomposition. Of course it should, but the Fourier series coefficients exactly stay the same as they are over here. The only difference is that although the Fourier series coefficients, the indices do not change, the frequency is scaled as we would have expected it to. So if alpha, for example, is greater than 1, you would expect an increase in the frequency because alpha greater than 1 is actually a time compression, and therefore that correspond to the increase in frequency. On the other hand, if alpha is less than 1, is between 0 and 1, if it's between 0 and 1, then you would expect a time expansion, and which would correspond to a decrease in the frequency, as you can see through the synthesis equation as well. And the same thing applies whenever, even if alpha is negative, and I'd leave that off for you to think about.